Okay, so the next thing I want to discuss with everyone, and again, these are concepts that we are going to use repeatedly in the course, and I just want to make sure that everyone's on the same page. The next concept that is important to talk about is confidence interval. Now, I'm sure that many of you have read research papers, and in the research papers you've read that the confidence interval, 95% confidence interval estimate for the population mean is somewhere between, say, 33 and 42. So you'll read a statement like that, and then you wonder, well, what does that mean? What does it mean that the confidence interval is this? Now, a lot of us have ideas about what confidence intervals mean, and I would suggest that a lot of us have the wrong idea what a confidence interval means, because in my opinion, confidence intervals is one of the most commonly used statistical methods, but one of the least well understood concepts in statistical methodology. So to see what it is, let's think about the guy in the basement again. And let's suppose that every day, this guy, every time he takes a sample from his population, he also constructs a confidence interval. Now, the way you do that is to construct a confidence interval, you take the sample mean, and you add a certain number of standard errors of the mean. Remember I told you that the sampling distribution has a certain shape, and the shape is normal, and it has a certain variance, and we know that the variance of the sampling distribution of the sample mean is the variance of the observations divided by n. So this is the standard deviation of the sample mean, is the standard deviation over the square root of n. So this is how you build a this is the t-distribution. Again, to use a t-distribution, you have to assume that the original data were normal. So this is the way you construct the concept. You take the sample mean plus this, and then you take the sample mean minus t times the standard error. Okay, and this is the definition. This is how you construct a 95%. 95% would mean that you would take the upper 97.5 percentile of the t-distribution with n minus 1 degrees of freedom. But this is how, and again, I'm assuming that all of you had a first statistics course somewhere and that this is not a new concept. Okay, so the first day he takes his sample, he constructs a confidence interval, and say it looks like this. Again, here's the sample mean, and the sample mean plus t times the standard error, and the sample mean minus t times the standard error. And the next day he does it, he got a smaller variance, so his confidence interval is shorter. And the next time he did it, he got a very large variance, so his confidence interval is wider. And day after day, he computes confidence interval after confidence interval. Every time he takes a sample, he computes another confidence interval until he's got 10 million of these. Okay? Now what he has also, which none of us would ever have, is he has that disk. And that disk tells him what the true population mean was. Now when he's constructing a confidence interval, he's trying to say that he thinks the population mean is between here and here. Or the second day is between here and here. But let's say that the true population mean was right here. This is the true population mean mu. Okay, so you see it? That's the true value. So on day one he said that he thinks the true population mean is between here and here. So was he having a good day? He was having a good day because the true population mean was inside the interval that he said it was. On day two, was he having a good day? No, he wasn't having a good day because his interval didn't include the population mean. Did he know that he wasn't having a good day? He had no idea because he doesn't know what the population mean is. Okay, on the third day, was he having a good day? Yes, he was having a good day. Did he know that? No. Again, he doesn't know that. He just built a constant interval. Day 4, was he having a good day? No. Did he know that? No, he didn't know it. Day 5, was he having a good day? No. Did he know that? No. See, that's the beauty of statistics. You don't even know if you're having a good day. You just keep doing your thing. You go about building your confidence intervals. You have no idea whether the confidence interval is covering the true population mean or not. But what we do know is that if you do this process 10 million times, 95% of intervals that you construct that way cover the true population mean. And so you can see, in fact, the definition, see if I can, in the slide, the definition is, again, here. The definition of a 95% confidence interval is upon repeated sampling, 95% of intervals constructed in the same way will cover the true population parameter. And by the same token, 5% of them won't. So 5% of the days will be bad days. 95% of days will be good days. What happens if you think that that's not acceptable? I don't want to have bad days 5% of the time. What can you do? Well, one thing you can do is instead of building a 95% confidence interval, using some number in here that represents 95%, you use a bigger number in here and you have a 99% confidence interval. And that would make this interval wider than it was for a 95% interval, so that this day would turn into a good day. Again, did you know that? No. You don't know if it's a good day or bad day, but by making a wider interval, you know that more of the days will be good days than bad days. Okay, so that's a 95% confidence interval. 99% confidence interval is wider. Okay, and so again, the definition is upon repeated sampling, 95% of intervals constructed in exactly the same way would cover the true population mean. Once you write down the interval, it either covered it or it didn't. It's not 95% probability of being correct. We call it a 95% confidence interval. And the word confidence is used in a very specific way. It relates to repeated sampling. It relates to the idea of sampling from a population over and over, such that 95% of intervals constructed in that way will cover the true population value. I want to reinforce something that I had said before about confidence intervals and why they're called confidence intervals. So a student of mine gave me this example, and I think it's a really terrific example. He said, let's suppose that I was a deep sea fisherman, and I had actually I had an underwater farm where I raised oysters. And we know from many years of experience that 95% of all oysters that I bring up from this bed contain a pearl. So 95 out of every 100 oysters that I bring up contains a pearl. So let's say that on a given day, the fisherman dives down and he collects exactly 100 oysters, puts them into a bag, brings them up to the surface, and puts them on the desk. Okay, now I've got 100 oysters in the bag. And he says to you, listen, I'd like to give you a gift. You can take one of these oysters. It's yours. My gift to you, an oyster. So you say thank you, and you take the oyster. Now, the second before you took the oyster from the bag, you had 95% confidence that that oyster would contain a pearl. But the second you take the oyster and you go away, it either contains a pearl or it doesn't. So it's either going to be a good day or a bad day. Probability is 0 or 100% once you take the oyster. But before you took that oyster, 95% of the time you're going to get a pearl. So your confidence is 95%. The probability is 0 or 1. And so it's important to understand that the word confidence is used in a very specific way. You're 95% confident of getting a pearl. But once you have that one oyster, you either have one or you don't. And it's the same with the confidence interval. Once you write the interval down, it's either right or it's wrong. The confidence part relates to repeatedly sampling from the population and computing interval after interval, some of which contain the true population value and others don't.